Estimating the population mean. The most reliable estimate of mu, the population mean, is obtained from the mean of a random sample. And we've looked at this in the investigation and how when you take a larger sample, it's a better estimate and so on. But we've also looked at the fact that there's variability. And we saw in the investigation that we had one sample that was 225 and it was actually worse than the one of 25. So it is the best estimate that we have, but it's not always great. However, the sample mean x bar from any given random sample is unlikely to exactly match mu, and that's what I was just saying. Instead, we use a confidence interval to provide a range of values within which the population mean is expected to lie. So this is an important term, confidence interval, and you are almost certainly going to be asked to calculate confidence intervals in your test and probably in both exams coming up. For example, a 95% confidence interval for mu can be calculated by taking a range of values. So we have x bar, take away 1.96, you should recognize that value. We've looked at that value before. That is the Z95 value, and we looked at getting that from the calculator. Let's just quickly look at that again, I think. So let's see if I can find my calculator. Here it is. And in fact, that's the last calculation I did. So we've got the 0.95 and we've got 1.9599. That's the 1.96. So it's just rounded a bit. And we multiply that by the standard error, or if you like, the standard deviation of our sample for sample size n. And then we go x bar plus that same quantity, and that gives us a range of values. We'll look at that in examples to come up. This interval allows us to account for the variability inherent in sampling while making an informed estimate of the population mean. So instead of saying that our population mean is x bar, we're going to say the population mean has a 95% chance of lying between these two values. Note that Z95 is 1.96, we just looked at that. So we can change that for that value if we want a 90% or a 99% confidence interval, for example. We'll look at that a little bit later. A 95% confidence interval is a range of values that we are 95% confident contains the true population mean mu. Here's a simple way to think about it. Imagine you take lots of random samples from a population and calculate a confidence interval for each sample. If you did this 100 times, about 95 of those intervals would include the true population mean. That's what we mean by a 95% confidence interval. It's really important to remember that because I've seen it asked just straight out in an exam. It's not a guarantee that the specific interval you calculated contains mu, but it's very likely, 95% likely in the case of a 95% confidence interval, based on the data and the confidence level. In short, it's the range where the true mean is most likely to be based on your sample. And remember, samples vary. Another way of looking at this is that 95% of all sample means will fall within mu take away 1.96 sigma over root n, and mu plus 1.96 sigma over root n, where of course mu is the population mean if known. This is illustrated in the diagram below. In the top part of the diagram here, we have a normal distribution based on the population mean, and here we can see the confidence interval based on that, with mu at the center, and then take away 1.96 sigma over root n, so that's a 95% confidence interval, and at this end plus 1.96 sigma over root n. Below here, we've taken a sample and we've got x bar. And here we have a confidence interval that is based on our sample mean. And notice that they're not the same. They are the same width because we've based them on the sigma. So this one is x bar take away 1.96 times sigma over root n, and this one x bar plus 1.96 sigma over root n. In this particular case, this confidence interval down here based on x bar does contain mu. We can see it is here within the interval. But we know that only happens with 95% of them if it's a 95% confidence interval. The confidence level is the amount of confidence we place in mu being in the calculated confidence interval. So some usual confidence levels that are used are things like 90%, 95%, and 99%. And if you look at the confidence interval, you can see they're all based on a multiple of sigma over root n. So x bar minus that, x bar plus that. And all that changes is the z-score value for the level of confidence that we have. And we should have seen all of those values before. Other confidence levels can be calculated using the appropriate z value. Consider samples of different size, but all within mean. Consider samples of different size, but all with a mean of 10 and coming from a population with a standard deviation of 2. The 95% confidence interval is 10 take away 1.96 sigma over root n to 10 plus 1.96 times sigma over root n for various values of n. Look at the diagram. Look at what happens as we increase n. This should not be surprising since n is in the denominator, and if we're dividing by a bigger number with sigma staying the same, saying as 2, so we've got 2 over root n, as n gets bigger, this quantity gets smaller, and therefore the confidence intervals get narrower. This shouldn't really be a surprise once you think about it like that, but it's important to note that because it's a question that regularly comes up in tests and exams. Increasing the sample size produces confidence intervals of shorter width. We can see this because of the structure of the standard error, sigma over root n. Since root n is in the denominator, increasing the value of n whilst keeping sigma constant will decrease the value of the standard error, thus reducing the width of the interval. As I mentioned, this is an important concept that comes up in many assessments. The other factor that affects the width of the interval is the confidence level, and again this is regularly asked. Note that for a 90% we have the following. We have x, that should be x bar, plus or minus 1.645 sigma over root n. But when we move up to 95%, it's now x bar plus or minus 1.96 sigma over root n. So this quantity here is going to be smaller than this quantity here. Now it makes sense because if we make it wider, we can be more confident that the true mean is in there. So for a fixed value of sigma and a fixed value of n, the 95% interval is wider than the 90%, and the 99% would be wider still.